right now. How many are there? 215. Just one more, two more minutes. One more minute.
Okay, sir. Okay, fine.
Okay, I think you can start the numbers. Let me see once again. 240. It's not crossing 250. Okay, I think almost 10 minutes passed, so we'll start. Um, Hello everyone. I hope you can hear me loud and clear. So let me start the presentation. Yes, I think you can see my screen. Yeah. Right. First thing first, let's revise what have we done in the yesterday's class. Very good afternoon to all of you, all the participants, organizers. Okay. So yeah. Right. Uh, this is the point where we started. Okay. Poisson statistics. Right. You see an expression here which tells me about the number of photons could exist in a particular mode of an electromagnetic wave. Okay, where the modes which I have chosen is a coherent light source mode. The alpha kits, what you see here, alpha kits. Okay, in a particular mode, how many number of photons would be present if I had to find? I'll be finding throughout all the modes, so it becomes a probabilistic. Okay, it's like if I have a basket of different colored balls. In that basket of colored balls, I'll just pick uh, one ball. So one ball in the sense I would be getting particular colored ball. With let's say six colored balls are there, 1/6 is the probability. Something like that. Here I'm just trying to pick the number of photons could exist in a particular coherent state. Okay, where alpha ket is the coherent state. Okay, so the number. Okay, so maybe I can use my hand note quickly. Okay, right. Okay, so the coherent state is there, which can have, we don't know how many number of photons it can have. It can have no photon, it can have one photon, it can have two photon, it can have three photon, and so on up to n photon. So each one comes up with a probability. Okay, so that is in a superposition. So if I had to find for a given mode with n photons, right, in generic n, what it would be, I'll just take a inner product with the, see here, all these are the base states, just like 0 ket and 1 ket for a 2 qubit system. I'll get, this would give me the probability Pn. So I'll just square it. So I'll get the so I'm sorry. These are like probability amplitudes. I should give it the different probability amplitudes. I'll say alpha 0, alpha 1, alpha 2, alpha 3, alpha n. Maybe I'll get confused with the alphas. So let me call it as A0, A1, A2. That would be easier. A3 and A4. Okay. So I would be getting here is what I would be getting, an whole square. Okay, an whole square. That is what I get. So that is interestingly happened to satisfy a Poisson statistics, which would look like alpha square n factorial exponential minus absolute alpha square. This is a number. Okay, right? So now by varying alpha, okay, going from different mode to mode, I can find out what is the probability of number of photons in it. Okay, so interestingly, I can find also the average number, means expectation value of this is exactly equal to the variance. Variance. How do I write variance? Gradient, like something like that. Okay, both are equal, current state. In that case, what it means is the average and the variance exactly equal. So then about the average, there are modes which are close to average number. Means there is a, when I want to pick exactly the equivalent to average number of photon existing mode, I would not be succeeding because there is one guy nearby. Okay, so this is a correspond to coherent state light source. Coherent light source. Here I can succeed in picking a single photon up to some extent, but not 100%. Okay, if I have a photon statistics where, okay, the average number much larger than the variance. Okay, variance inside. If this is possible, that means your photon statistics will have nice single peak, and if we try to find the variance, it is almost 0, right? So in this case, what I mean is I can pick exactly the specific number of photon existing mode. This is actually okay, coherent source we have seen. This is actually flow state, where the number of photons is fixed, which cannot go out or come in. Or it's also called sub-Poissonian. Okay? It is very much suited for single photon emission or single photon sources. Okay, fine. So that is what we saw last time. Now, apart from Poisson statistics, there is something called correlation measurement. What I mean by that is, if I have light source, if the photons are coming in bunch, okay, if I just look at a different space, okay, right, and a different space or different time, let's say in different times, okay, so time I can separate, or so at some point I'll have 2 photons, at some point I have 4 photons, right? So I can just find out how many number of photons are there in time separated. So photons, sum of photons would I connect it to the intensity. How many photons comes at time t multiplied by, let's say how many times photons comes slightly later than that. Let's say separated by time tau. Okay. So let's say let me find the average such thing. Okay. I'll do the same experiment several times, and then I square. Okay. But if this is equal to 1 means what? There is no difference between number of photons coming at time t, number of photons coming at later time. It's a nice stream of photons. Same number of photons coming time to time. So I can do something with that. Okay. So this is actually G2, the correlation function. Fine. That is what I meant. Correlation measurement. So it has to be like 1 per better, or yeah, and it may go worse if the numerator is large. Okay, and that means g of 2 is greater than, or sorry, just greater than 1. So what I mean is it is a classical field or a thermal field. If it is less than 1 means it is something other than the light source which I want. Okay, so that is the second order correlation function G2. And there is something called Mandel parameter. We see there is a small experiment on that also. Okay, and this is also involves a variance and the average number. Please excuse me for using expectation value of number operator. I'll write like this. Also, I'll write like this. Okay, right? So, and when it comes to variance, I might use like this, or like this. Okay, more or less both are same. What I mean by delta n is, if I have an average photon number and at randomly I'll pick one mode and find how many are there, how much it is varying from the average. This is the delta n. And such thing I can do for all the modes. Okay, and square it and find its average value. That is the variance. Okay, and I'm just all the way compare the variance with the average photon number. Okay, fine. So now we did that, and there is something called Wigner function. I gave you Wigner function description here. Okay, Wigner function is just a something just very close to, appears like a wave function absolute square. Okay, right? And if the Wigner function, see here is a plot, it's a if we integrate over x, we'll get, so okay, so anyway, this function, you would not worry too much about it, but what it conveys, if the Wigner function is greater than 0, it is a classical light, and if Wigner function is less than 0, it is a non-classical light. It could be quantum in nature, The moment quantum in nature means a stream of photons having bunch of few photons. I can separate them using some beam splitter. Few photons going here, few photons transmitted here. If I have a beam splitter, 50-50 beam splitter, okay, right? Just like a mirror, partially silvered mirror. So partially silvered mirror, few photons go through, few photons wherever it's silver part, it reflects. Okay, so that is kind of material I use. I can just separate them if it is a non-classical light, right? Okay, now single photon generation, we did discuss few things, right? That is a Raman based scattering we discussed, right? So Raman based scattering means it can be spontaneous, it can be stimulated, or it can be some cavity enhanced Raman scatter or Raman transition. Okay, so here, right? So the Raman scattering means what? Okay, we didn't discuss yesterday. It is an inelastic scattering. Inelastic scattering means elastic scattering means nice two points comes and hits each other. Probably they may deviate 2 points, and whatever momentum and energy with which they are coming, okay, with the same momentum they will go. Probably the direction is changed. With the same energy they go. Okay, even this one, M2, V2, and E2. This guy will go with the M2, V2, and E2. No issues with that. So it is an inelastic. It's elastic. Elastic collusion. Okay, something like something stretches, comes back. Means there are no loss in any structure of the system. But if I have inelastic collusion, inelastic, what is going to happen is probably this guy will come and this will come, they hit each other, they go out. But this guy goes away with the energy less than what he has in the initial plane, initial time. Okay, and same is for this guy. Okay, right? So E1, E2 would be less than what is the previous. That means the energy is lost either to the surroundings, okay, or energy maybe one guy got, okay, and if overall energy between them remains the same, that is still elastic, right? So one guy got and he loses to the surrounding, that is also shown to be inelastic, right? There is some loss of energy means inelastic. So the Stokes and anti-Stokes of Raman scattering exactly belongs to that domain. Okay, what is it is, I just start with the 3-level atomic system. Okay, right? So there is something called a ladder atomic system. Just like ladder, this is a 0, 1, 2. Okay, ladder atomic system. Again, this is 3-level, and only I have just chosen in such a way it suits my description, whatever process I am talking about, right? So what it means, there is a nucleus here. Okay, so the orbits are like that. Okay, and the only thing I have just taken a snapshot, like in small part of it. Okay, and same thing. See, this is a ground state, second ground state, and the excited state. Okay, so if I just, instead of taking one over the other like a ladder, I can just put them two separately and take it becomes a lambda, capital lambda. So this is called 3-level system in lambda configuration. Okay, and there's only in the lambda configuration what people choose, whatever two ground states are chosen to be very close to each other. Okay, so they are almost like two ground states. Okay, So that is what the lambda for you. But when it comes to ladder 3-level system, there the first two ground states may be separated with a greater extent. So the separation would be very good compared to the lambda case. Okay. So here I will call this as a first excited state. This is a second excited state. Okay. Why I'm explaining? Because we would be needing those things for some discussion for today. Okay. Now I have a lambda system. Now for the lambda system, right? I supply some energy for the electron here. It goes all the way to excited state. Let me call U, E, and G. Okay. This energy goes through. Electron cannot stay there forever. It might come back to U, or it might go to G also. That possibility is there. So when it comes to G, it emits the photon having energy separation between E and G. We supplied energy which is much larger than that. So some energy is lost. So it is inelastic Raman scattering. Okay, inelastic Raman scattering. Using which I can generate single photons. And you might say, you are, first of all, you are sending photons, that itself could be taken as a single photon. Why you want to do this process? Remember, when I'm sending a pulse of photon matching this separation means it might be having so many photons, but only few photons go and talk to these atoms. I will take very few atoms, let's say atomic vapor. People say atomic vapor means hardly one atom surrounded by one more atom, right? In this case, even if I send a bunch of photons, those all photons would not react with all that. So one atom get excited, that emits this photon, and other one emits in this direction, and one emits in this direction. So literally, if they are emitted in a solid angle, okay, right? So I have to catch in which solid angle the photons are emitted, single photons of particular frequency are emitted. That I need. And one more is also happening in the same solid angle. What is that is, same atom may decay back to you and send much larger photon. Okay, so much larger photon would be something in the same direction. So I don't want to get confused with that. This one, the energies are separate, but I'm not interested in the first place. What are they? Okay, right? So I have to catch the particular one which I want in that particular solid angle. Since there are so many coming out, it becomes a probabilistic in nature. Okay, unless I don't have a good equipment to catch, I would not get succeed in this spontaneous Raman scattering. Means I have to wait for the spontaneously happening here. Okay, so there's other physicists thought, why don't I trigger this transition as per my wish? Okay, right? So for that, what they did, addition to adding some pump field omega p, capital omega p, it's called the Rabi frequency R, which is connected to the amplitude of pump field having some omega frequency. Now there is a ground state here. In addition to this, I will also have a stored field omega s having omega s, capital. Okay. So here in this case, there is a very good chance, if at all if there is an electron somehow comes here, there is no other go. There is some kind of a vacuum tube is created here. You guys probably know Hyperloop. Back then, this Elon Musk has come up with. So how they work is, there is a tube where the vacuum is maintained. So if you just put anything here, it is sucked towards this direction. Okay, and no resistance absolutely. Okay, so that is the idea. So I like say some kind of a vacuum tube is created, if there are any photons, they have to drop here. Okay, that's a crude way of saying things. Now, what is exactly happening is, like yesterday, so many people were asking, there is a detuning, a mismatch of signal field and the pump field we will do. So the pump field is mismatched by some delta P. Okay, and this is sigma P, sorry, omega P, and this is also slightly mismatch. Okay, this is slightly mismatched. This is a delta S. Such a way, electron would jump from here to here, not go there. It just goes here, and there is no way. This guy would not let this go anywhere. Tells that to go back here. Okay, so the population is being transferred from U to G along E. Okay, adiabatic transfer. So adiabatically it is transferred slowly, step by step it is transferred. And why this guy will leave? This guy will leave something which comes into it, he will give rigid, right? But not. This guy is kept at sufficient level so that this guy doesn't bother. If somebody comes, somebody goes, he will not keep quiet. Okay, he will keep quiet. So there is another way, another process called coherent population trapping. Coherent population trapping. It's a quantum optics process, and also there is something called electromagnetically induced transparency. Okay, so using these two together, we can make light transparent to a particular medium. How? If light is not transparent means some electrons are there observing the light, no? But we'll just put all the electrons in a particular level, okay, and trap them. It will become a dark state. Something enters into the darkness, can't come out. So the electrons were put into the dark state. The moment they go, they can't come out. So if there is any further light comes in, there is no electron to absorb. So in that way, I would see something called electromagnetically induced transparency. And I would see there is a coherent population trap is there. So this E level is like that. It's some kind of a trap level. It is shut the door for everything. It will not let anything to come in. It will not come or anything to go out. At the most, if it lets somebody to come in, same equal number, it will allow to go out. That is what the slightly different version of CPT here in this particular situation. Okay, so with this, I am able to create a photons emitting with the energy difference of level E and G throughout the session or throughout my requirement. Okay, so that is a STIRAP for you. Let me get back. You can understand even mathematically why energy state E acting like that. Because if you just carefully see, for this kind of a STIRAP Hamiltonian, okay, this is a spontaneous, okay, for a STIRAP Hamiltonian like this is internal Hamiltonian, it's not, okay, and the interaction Hamiltonian would this kind. For this kind of a Hamiltonian, at a given point, what is the energy state of a system would look like? That is given here, psi naught equal to cos theta u minus sin theta into g. This is at a given point in time, what is the state of the system. How did I get this? I have Hamiltonian, remember. I just find the eigenvectors of that Hamiltonian and eigenvalues of the Hamiltonian. Okay, fine. So this vector, you guys see, please see, this vector what I have, I can represent on trigonometric axis and find what is the angle which I have here. Okay, so the angle I have here is tan inverse omega p by omega s. Right? Remember, that is very, very crucial. Now, when I go actual processing, initially, let's say I start the quantum state with a u. Okay, means atom is in the ground, the lowest ground value state. Okay, right? So initially I start the system in u, means electron is in u. Fine. Now I switch on. So when there is nothing outside world, outside interaction, the Hamiltonian is H naught. When I switch on the interaction Hamiltonian, means I am switching on the field onto the atom. What is that I'll do? I just do a Stokes field. Remember, first I will do the Stokes field. Later I will add a pump field. First is a Stokes field. That is the strategy for a STIRAP process. When I add a Stokes field, you see tan theta I have equal to omega p by omega s. You see, right? Tan theta is omega by p by omega s. Now, what this is saying, I don't have any p in the first stage. I have omega s, which is not equal to 0. But this is equal to 0, by the way. So tan theta is 0. When do I have tan theta equal to 0? That is when sin theta equal to 0. What is that theta value? Theta might be 0. Okay. So the quantum state at any given point, what it would look like, it looked like cos theta u minus sin theta g. That is the quantum state corresponding to the Hamiltonian what I have for a STIRAP process. This is a, okay. I am not writing the theta explicitly. Theta is actually a combination of the field strengths. Okay. Now, as per the field strength, this is 0. So the quantum state which is evolved is cos of 0 into u. Okay. So in that case, I'm still in u. Okay. Now, what I'll do, I'll immediately switch on the pump field. Okay. Right. So this time what happens when I switch on the pump field, omega p becomes 1 and I just switch off the omega s also. So 1 by 0 is actually infinity. That means the tan theta becomes infinity when cos of theta is 0, that is theta is pi by 2 or sin theta equal to 1. What is this situation is implying to me is, as per my quantum state, the evaluated quantum state would be minus g. Doesn't matter, minus sign is there. This is a probability amplitude. If I just square, it becomes first relative phase. I don't need, sorry, absolute phase. I don't bother. So this way, the way I switch on omega s first, omega p later. In between, when I'm just talking, I'm not talking about, well, let's say both are present. In that case, the overall quantum state would behave like cos theta with respect to time t, u minus sin theta of time t, z ket. This is a quantum state. Now it's up to you how you switch on your field strengths, and accordingly you can play with where to put your population of the electrons, whether you want to put here or here. By the way, this is not coming into the picture at all, because that is how I chosen my Hamiltonian. Okay, fine. So now let's go to the next part, that is we discussed. Okay, so I said there is a way I can obtain even the entangled photons using this technique. Okay, fine. So I have a few things to show today. I said I will tell you how do I generate, or how do anybody can generate a single photons using experimental technique. Okay, so I just borrowed the paper, borrowed the pictures, and also I studied the material or the journal which is mentioned here. It's a review of modern physics, right? Okay, so if I am talking anything, that is from here. So I'm citing here. Okay, let me go there first. So there is something called Hanbury-Brown twist interferometer. Remember, the moment if I say interferometer, please straight away recollect that it is about interference. Something is interfering, and I'm just setting up a setup where the two things come and interfere. They can interfere constructively or they can interfere destructively. Okay, so what I mean by constructive interference, let me just slightly recollect. Let's say you studied the Young's double slit experiment. Let's say I have a source, light source. Again, it sends the light out. Then coherent light source, remember, coherent light source, CLS. I have a mechanism where there is two holes. Okay, right? It's called double slit. Two slits are there, and only through the light holes only light goes through. So if I have this kind of a setup, what happens is this whatever this hole is there, that itself acts like a light source of its own kind. So this is a light source again. Only thing is this light source and this light source borrowing light from same originator or same source. So they have coherence time. Okay, coherence time means if I just take a light going like a wave, I'll just find what is happening at this point, what is happening at this point, separated by some temporal time delta t. There is always a connection between this guy and this guy. And if I just slightly shift this, okay, again I'll just take delta t time there. Okay. Now if you see carefully, see at this point this guy is just reached maximum. This point this guy is reached maximum, right? So they are in sync. They just reach their maximum. The next thing for both of them is coming down. Okay, so both guys are in sync. And now just to see this point and this point, separated by same time span. And this guy is about to take a hill head on, and this guy is also about. So the same kind of a pattern is there for both the guys. So I'll say there is an in phase, or if there is a small phase difference is there, okay, right? So that phase difference is maintained despite of my time span wherever I take, right? So this is 2 points where I've taken in phase points I've taken. This is temporal separation. Even I can do spatial separation. In a spatial separation, if I do that kind of a same coherence would be there. Okay, so the light which is coming here, would have that kind of a spatial correlates. Now, for a double slit experiment, let's say I have a screen here. Okay, now if I just take any point, the light would be coming from here and hitting there. Okay, it is hitting from the bottom. You see, it is hitting from the bottom. Now, light coming from here and hit from the top. You see, the first guy is trying to increase from the negative to positive. Second guy is coming from the positive going to negative. It's completely out of phase, 180 degrees out of phase. It's like two people just crossing each other. This guy is going this way, this guy is going this way. There, if you let them hit head on, there is a serious damage. Since they are exactly equal, this is the point where I see destructive interference. Okay, that means whatever energy which is both guys are coming, they're just nullifying each other. This is an interference. Okay, so there are places both guys could hit with in phase. The top guy also hits in phase, so bottom guy is also hit in phase. So in that case, I'll have constructive interference. Okay, so this can happen even for single photons. It can happen for multiple photons. It can happen for, it happens for coherent light source having so many photons. It can happen for single photons. Now, what I was trying to explain here is, if I have a single photon source, okay, if it is not a Fock state, okay, Fock states are what? Fock states are very, very rigid states. Means if I take n equal to 1, a Fock state with 1 photon, if I prepare that guy and send along, that guy always goes with the same state, same single photon. No other guy it allows to, no other guy to come in. Okay, if this photon is having, let's say, 100 joules of energy, okay, energy separation is 100 joules. Usually what happens, that guy can split it to 250 joules and 250 joules and become two photons. Okay, that is a splitting. So even that would not happen with this kind of a Fock states, right? So that kind of a stability I have if I prepare the information using the Fock states and then send the information along, nobody else can fiddle with that. If somebody fiddles with that, I really know exactly what somebody is trying to do. Okay, now coming back to this setup, what I have here, okay, I want to have a schema generating single photon sources. Okay, but I don't have Fock states every time. Okay, so let me show what I right. Yes, this one, not this one, this one. Yeah, here you see thermal source. I have bunch of photons coming. There is no regularity there, so I can't talk to them. I can't use them for a precise purpose. Okay. If I have coherent source, it is fixed trend. Like say it sends a bunch of photons, but it also sends single photons in between, right? So only thing is I have to hit the right node where I, like people say, you have to hit the right node. Okay, so I have to take that particular single photons. How do I do? I am using a beam splitter there. You see beam splitter I'm using. Okay, so that is the technique you are going to use here. There is a 50-50 beam splitter is used. Okay, and I can check whether there is a correlation or not. If the photons are separated in time, if there is a correlation is existing, are they coming together or not? If they're coming together, let's say, I can ensure that one photon going towards the detector, another photon going towards the B, and I can just get to some correlation function. With the correlation function, this is called, this counter is there. It counts whether the photons coming simultaneously or not. Now, interestingly, if I have only single photons coming at a time, in that case, there is no way I will detect photon at both places. I will detect only at one place. Okay, so this is how you can ensure that the source is a single photon. This is how you can detect whether the source is giving single photons or not. Okay, right. Now, next, there is something called, okay, Tango Mondel interferometer, right? So if you get back, earlier I just said interferometer Mondel parameter. What is that? This Mondel parameter is there, na? See here, the third one, two, three, four, fifth column, right? So what is the Mondel parameter? It is a simple ratio of atomic photon number with respect to its a variance minus 1. Okay, if the Mondel parameter is 0, I would say it's reasonable, it is a coherent state. If it is negative, definitely it is negative minus 1. I'm going to say the variance is absolutely 0, right? So it has a fixed average number and it is a Fock state, and I would have, if Fock states prepared with single photons, I can have single photon sources. Okay, so that is actually understood from this experiment. Okay, so there is a beam splitter here. Only thing difference from previous case to here is I'm going to send, right, the light source separated somewhere, and those two parts I will send it into the beam splitter from either side. Okay, right? Now if there is a correlation is there, means that like the correlation means the photons which are coming from 2 and 1 direction here, if they're coming at a time, okay, then there is a chance of constructive or destructive interference. If they're coming separate times, they may not never reach each other and they may not interact with each other. In that case, I'll not have any interference pattern at all. So looking at whether I'm going to get interference pattern or not, I can say what is a correlation associated with the light source, which is subject to this kind of experiment. Okay, so if the light source is incident from direction 1 and 2, one is green light and the red light. Let's say, even though they come in time, they can go straight without being deviated. Okay, so there are 4 scenarios I have here for, let's say, like 2 coins I toss, both the coins should be head, both the coins should be tail, and one tail, one head. Okay, that's kind of 4 chances I have, and here I'm just talking about all the 4 chances, right? So depending on all the 4 chances, I can easily make out what kind of a light source I have, right? And also I can detect whether I can the detectors are single photon detectors or multi photon detectors. Okay, fine. So here you see in the A and B case, both the photons are coming in the same direction, whether towards the right or towards the bottom. C and D case means A and B are like I have head head or tail tail option. In the C and D I have head tail tail head options. Fine. So this is how you can, even if I use indestructible photons, means which I can differentiate. Even in that case also, this kind of a technique would allow me to find the whether photon sources are single photon or not through the photon statistics or correlation function. Okay, fine. So this is about the extension of what I discussed in the yesterday. Now I said even even entangled photons you can find using a process like a Raman scattering. It's not Raman scattering, remember. It is called a parametric down conversion. Parametric down conversion. Okay. So what it means, let me use parametric down conversion. Okay, or you can say second order or spontaneous, like SPDC, right? So that's what we said. different ways of generating single photons. Right here I say spontaneous parametric down conversion. Okay, right? So let's understand what is that. I just explained you earlier. I have two level atoms, and interestingly I have one more level also in between. Okay, I choose the atomic system in such a way the separation between here and here, let's say they're equal. Okay, let me write in terms of joules, 50 joule and 50 joule. Okay, now I have to supply a photon with the energy 50 joule so that electron would jump from ground to either first excited state, let me call 0, 1 and 2. Okay, one photon puts the electron from here to here, first 0 to get 1, and another photon maybe it comes in exactly same time, it puts into later stage. Okay, to level 2. So it has to be nicely synchronized. Let's say I don't have that kind of a synchronization in my source which is coming and hitting this atom. In that case, what I expect, if I supply photons of 50 joule, I would see electrons going in here and maybe coming back. Okay, and I can also choose the atomic system in such a way. If I supply a photon of 100 joules, you see now interesting thing. If I supply a photon of 100 joules, here in this case, the 100 joule photon could be absorbed by this electron. Instead of just it is going to the mid level, since this guy has got sufficient energy, he will go all the way to the top. Okay, not bothering, there's a midpoint is there or not. Now that guy can't stay there. There is a timeline 10 to the power of minus 6 seconds. That guy can stay there, microseconds. He has to come down. Now while coming down, okay, since I have a mid state there, I can ensure some parameters. I'll come back what are the parameters or some setup I can ensure. While coming down, spontaneously this electron guy would come to 1 ket and emit the 50 joule. Okay, and he cannot stay there forever, and again he has to come down and he will emit another 50 joules. So what I'm doing, 100 joule photon, I am dividing into 2 photons, right? That is what the down conversion. High energy is converted to low energy. It's like 1 photon coming through becomes 2 photons, just like a beam splitter. Okay, right? So beam splitter talks about a stream of photons probably, or a classical light. But here I am talking in terms of 1 photon coming in, chopping into 2 parts, another photon flow energies. Okay, so this is there are three waves are involved here. Okay, you might ask me only one wave is involved, that is divided into 2 parts. No, it is not the case like that. So there is one wave corresponding to this transition. There is another wave corresponding to this transition. Another wave corresponding to this transition. The 3 waves are there. It's called, that's why it's called three wave mixing. Okay. What happens here is, let's say this is called pump field omega p, right? So this is called signal field. This is called idler field, capital I. That is also same as signal, just to give a different name. So what exactly this kind of situation is possible when, let's say I have a vapor of photons, means atoms are there, a vapor of atoms are there. Okay, right? I just put them inside a cavity, means let's say some concave and convex mirrors are there, right? And now I just incident a ray of light stream or laser from one direction. This is omega p energy, angular frequency wise, and Rabi frequency or the strength is omega p, capital omega p, and this is of 100 joule each photon, right? and I'll send one more laser source from here, probably much weaker than omega p, and one more from here. Okay, so I said earlier there is a idler, okay, and there is a signal related. Okay, now the purpose of this guy and this guy is to just tweak a little bit to the atom so that whatever electrons, if they come here, has to just go stimulated emission. Stimulated emission 1 and 2. Okay, that's all. That is the purpose. Now if I send one photon from here, one photon from here 50 joules, one photon from here 50 joules. If I send, if you see 100 coming from here. Okay, right? Now what interestingly happens is this photon, one photon just triggers a spontaneous stimulated emission. That guy will go out, and this also, this guy will go out. Okay, where is this guy is going? This guy, 100 joule guy. 100 joule guy would just divide into two parts, and one more photon comes out like this. One more photon comes like this. What counts for me, the guy, this guy is divided into 250 joules. Na? That is the important for me. Interestingly, these two guys were created out of same atom, same photon. They carry some kind of a togetherness, some kind of affinity, some kind of a correlation between them. That correlation would look like this 0, 0 plus 1, 1 divided by square root of 2. If you recollect, this is a Bell state. Okay, so one of a Bell state, I can have different kinds of Bell states. Okay, so this is actually three-wave mixing. In this way, I can generate two photons which are correlated. So in the photon case, you may ask, what is 0 there? Photon doesn't have excitation or something, you can say. For a photon case, photon means electromagnetic wave. Electric field would oscillate vertically or horizontally. That means its polarization could be vertical or horizontal. For a given photon, I can have polarization kept horizontal or vertical. Okay, capital V, let's say capital V. Now, there are two photons which are coming. So in that case, both photons could be HH polarized or VV polarized with corresponding amplitudes. So this is a Bell polarization, Bell state entangled polarizations for given photons, two photons. Okay, fine. So now I was telling you about how do you ensure this kind of a mixing only takes place in particular way. It is actually given here. Okay, so let me go for the presentations. Yeah, am I able to increase the size? No, it's okay. Now, if you see on the left bottom B, you have a three-level atomic system where omega p pump comes. Omega is the signal and omega is the idler. Okay. Now I have a pump laser. Okay, right? And here they are not showing what is omega s and omega p in the figure. Okay, which can be understood in such a way that one photon would be emitted, the second half omega I would be emitted from the bottom with a solid angle. The other one is emitted above that, slightly displaced with another solid angle. Okay, right? And here, how I am going to ensure such thing is the propagation vectors of this pump field and signal and idler could be arranged in such a way I can have this kind of a matching. Okay, so this is actually non-linear optics. It needs a wave mixing, four-wave mixing, three-wave mixing, or two-wave mixing. All those things one has to understand. So That is this itself would take 2 to 3 sessions, so I'm not getting there. So I can just say I can create environment in such a way the photon gets divided into parts and comes out as two entangled atoms. So this is how you can create entanglement. Okay, just a minute. So how did I exit this? Okay, I should get to exit somewhere. Okay, 1 minute. I'll just do it from the keyboard. Yes. Okay. Now, so the last one is actually called. Now we just saw three-wave mixing, and the other one is called four-wave mixing. Okay. So only small difference from the other cases. I add one more wave. Okay. Again, I have to match the propagation constants of that also in the picture. Okay. So here I'll take a 4-level atomic system. What you see here is 4-level atomic system is there. Let me go certify. Okay, I'm not going anywhere. Yeah, right. So the 4-wave mixing here, you see, I have signal, I have idler, and I have along with the one pump, I have one more pump. That is a pump 1, pump 2. Okay, so atomic vapor is there. Pump 1, pump 2 comes from two different directions. Okay, and it emits two waves which are signal and idler with the frequencies probably very close to the pump 1 and pump 2. Okay, so only thing, the wave, the phase matching, it's called, the phase matching is done in such a way, right? I can specifically get a single photon, that is the level D, sorry, option D, or I can get entangled photon as per C. Okay, so the trick here is you have to take care of your propagation vectors of the waves which I am considering in this particular mixing scenario. Okay, right? So that is the experimental realization for you. Okay, so now quickly let's get back to the other topics which I wanted to discuss for today. So if you have any doubts, let's quickly see the chart, and then I'll get back to the next part of the topic. Okay, so I see some hand raised. Okay. Okay. You're asking me to go for a slideshow, huh? Yeah. So why I'm not going for a slideshow, let me tell you. I do use my hand note in between. So if I go to slideshow, it is not easier to come back um, to the required tab. Na? I'm using a browser. Okay. But anyway, I share the material afterwards. You can just see. Okay. Fine. Now, yeah, my voice is too low. I hope no, I guess. Anyway, I don't see any questions here. Oh, there's a question here. For a cascade emission, why does de-excitation not takes place directly from the second excited state to the ground state? Yeah. So yeah, it's actually a part of nonlinear optics. I can just avoid that scenario to happen. So how I'm going to do, there is something called phase matching conditions, which is actually shown here in terms of the propagation vectors. Okay, and I can choose the direction of the light in such a way. I would somehow cancel that kind of a transition effect. Okay, let me tell you what is the transition effect cancellation, right? So there is a interference, constructive, destructive, I told you, na? So there is something called quantum coherence induced interference. Okay, what is that is? Let me give you a figure. Let's say I have again 3 level atoms. Okay, right? So let's say electrons can go from here to here, level 0 to level 1 through level 2. Okay, so if you just see the transition possibility like this is one way of transition. Not only that, there is another way of transition also, that is directly. But let's say I can just forbid that. It is possible to stop that. Okay, what else is there? Only through 2. But only through 2, there are multiple ways this electron can go. What is that is, without doing any oscillation between 1 and 2, it can directly go in one shot. The other one is going from, let me draw another figure that's easier to understand. The other one is going forth and come back and then go down. Okay, this is a transition possibilities. So it made one complete round and then drop down. Okay, that is one way. And it can make 2 rounds and then drop down. It can make 3 rounds and drop down. Those are all higher possibilities. They may not happen, but the make 1 round and come down possible, because the strength of the field which I applied here, like say Stokes field, that would ensure that kind of a round rotations. Now the transition from 0 to 1 can have multiple, right? So let me take the combination, the sums of all of them. Okay, so since they're quantum in nature, interestingly, they can destructively interfere each other, the transition. At some point, what can happen is, because of destructive interference, if you try to put electrons here, from here, they never come there, they never come to G, they will only go back to here. Because the transition going all the way from here to here, there are so many possibilities. This one and this one are destructively interfering. There is no way they will come down. So that is actually cancelled. Okay. So in the same way, you're asking question is, okay, so something which is excited, okay, why that is not coming back here itself? Why it will go to the next? Okay. So whatever electron jumped here, why it is going to the next? Because when I supply energy in such a way, this guy is even going above than 1 and goes to 2. While coming down, there is nobody to just tell him to whether jump to the next or jump to the here. It's spontaneously happening. While doing spontaneously, the mid states are there. They may appear to that way. Okay. So now 100 photon is coming, observed, and there is a chance of 100 photon it's also coming out. Okay. So when I have atomic vapor, when I send 100 joule single photon, I have multiple possibilities. One is 100 joule comes as it is, absorbed, emitted. And another possibility is 100 joule comes in, leaves the 50 joule out once, another 50 joule once. That is also possible. Means splitting. 50, 50, 100. Okay. Whether it has to go straight or get divided, that is, I can create a scenario using wave mixing and there's something called phase matching conditions. Okay. Yeah. For a cascade emission, okay, this I answered. Is it conventional to take 0 as a ground state, 1 as active state, or is it flexible? Is it 1 carries more energy than 0? Okay, let's see. The question is very simple. For me, the one which is close to nucleus is always ground. The one is away from the nucleus is excited. It's up to me what I will label it. Okay. Naturally, what is what? The one which is close to nucleus is a ground. One is away from the nucleus is excited. Okay. As it's all started, somebody started ground, calling it as ground as 0, excited as 1. Right? You can choose the other way around. You can say ground is 1, excited is 0. You can do that. But thing is, you have to stick to the calculation throughout like that. Whatever quantum computation mathematics you do, you have to stick to that. And while you are talking to somebody else, you have to check with them what is the convention they are using. And if they are using something else other than what you are using, you have to convert your results into their convention and then tell the results. So this kind of a always the hustle will be there. So people thought the lowest state would be 0 and the excited state is 1. Now coming back to the one more follow-up question for that. So there is 0, there is 1, there is 2. For a cascade system, I just say 0 is ground state, the 1 is first excited state, and 2 is second excited state for a cascade ladder system. Okay, for lambda system, the way the lambda systems were chosen, they are not chosen from the cascade kind of atoms. Okay, for example, rubidium itself, in the rubidium itself, there are atomic levels are well spaced, and there are atomic levels were very close, and there is a one excited state. So here I will do replace this, put this here, put this here. Okay, right, let me remove a part of it. Okay, it will remove everything. So there is a excited, there is a two grounds. So this is 0, this is 1, this is 2. So these two together called the pair of two ground states. Okay, 0 may be much lower than 1, but they're very close to each other. They're two ground states. Okay, right, and transition between 0 to 1 could be forbidden. We can do that kind of a situation you can create. Okay, no, it's 20 minutes past 3. I have to. Okay, will the resultant photon frequency be the sum of frequencies or difference frequencies? Depends on what kind of a wave mixing you're talking about. What is your result you are targeting towards? If you're targeting towards entangled photon from one photon, in that case the emitted photons will be half and half of the incident photon, where the emitted photons will be entangled. What is the deciding factor for photon to take certain path? Is it random or only probabilistics can be measured? Definitely it is random because it's a nature, nobody can dictate it. Okay, right? So there are various possibilities, but we can induce some possibilities, particularly even for three-wave mixing, four-wave mixing, which I am talking about. Whatever scenarios which I said, there is a split happens, entangled photons I'll get. See here in this case, in the four-wave case, I said I'll get entangled photons now. I'm not saying for every single 100 joule photon I'll get to 50 joule photon. It is not like that. Experimentally, it is very tricky. So in some thousands of photons which I'm sending in, out of 2-3 photons probably will split up and give me the entangled photon. So I have to have an equipment to exactly capture where those photons are spaced temporally and spatially, and then I have to wait with my detector to capture them. So theoretically, people say I just get the entangled photon. So experimentally, it is not that easy. Okay, right? So what is the deciding factor? That's what I said. The phase matching. Okay, propagation vectors you have to match. There's some you have to match. There is a difference. There is match. So it's all nonlinear dynamics. Sorry, nonlinear optics. Slightly tricky. I'll suggest there is a book by Nonlinear Optics by Robert Boyd. Okay. Okay. This is like Bible for nonlinear optics. It talks about everything related to atom field interaction in nonlinear fashion. Nonlinear means we usually think that if I apply electric field, okay, positive plate, negative plate, okay, there are atoms. If I apply, they create a polarization in a given polar materials. Polarization means if the polar material is there, nucleus and electron cloud, so it becomes a dipole, positive, negative, because of stretchability. Okay, polar materials, and creates a polarization. Okay, and usually we think that the polarization which is created is directly proportional to the electric field. Other way around. But in nonlinear material, nonlinear way, the polarization may be not linearly changing with applied field. So it may be go quadratic, or it may go more than quadratic powers. Okay, that is because of there is something called susceptibility, the chi, non-linear chi. So usually it is a linear chi for materials, for non-linear materials. Okay, right? So it might go order of second order or third order or so on. So again, please refer to Nonlinear Optics by Robert Boyd. Okay, so yeah, so let me get back what I want to discuss today. Atomic clocks, right? So yeah, I think I can go for slideshow here. And if I go to slideshow, so this is a problem. If I want to get back handnote, it will not allow me quickly to handnote. So I'm using a tab. Okay, right? So that is a problem. That's why I. Okay, let me connect mouse to the tab and then see. Right. Give me a second. Yeah. Okay. I think this is better. Okay, quickly I can. Okay, with a mouse, I'm better. Okay, so atomic clocks. Right. What I want to discuss. Atomic clocks. There's something I just like a sensors. I use atoms to do some counting. I use clock for what? I want to count a duration. Let's say from the sunrise, what is the duration I have passed till time today, up to now today. That is, to just specify that I need a duration. I need a duration. Okay, right? So to count the duration, I need something. Let's say back then there is a this hourglass. This Middle East people hourglass clocks are there, na? Okay, so there is a sand at the top, sand at the bottom, with the two kinds of cups connected in between with a small small pipe. So if the sand is up, you start the sand start pouring from the top to bottom. It will take some say 10 minutes to pour all the sand from top to bottom. Here I'm saying 10 minutes. It's just straight away comes. So what is that 10 minutes for you? Okay, if I say 1 second, what is 1 second for? What can happen in 1 second? Okay, the simplest thing you can do, I just like close my eye and open, flick. I would say I does this with a certain time amount of duration, that I call it as a 1 second. Okay, so I need something to measure time and any activity duration. Okay, so what I'll do, I'll just use how much time I'll take per flicking my eyes. Okay, so that I take it as a unit, some unit, let me call a second here, and I describe everything else in terms of that second. Okay, what I'll do, I can't say how many times I can flick my eyes from the sunrise to now is in 1,000 times, maybe lakh times probably, if I just say. So I can't say 1,000 lakhs of my eye flicks I passed time from the sunrise. No, I can't say that. So what I'll do, I just do the scaling up. I just say 60 times I can flick my eyes. It is equal to, I call it so 1 minute. And 60 times those 1 minute, I'll call it 1 hour. And now I'll say from the sunrise, how much time is fast is there right now it's 3:28. I said 3 hours is 3:28. That is so let's say sunrise at 6 o'clock in the morning. So there is a 6 plus 3. There is a 9 hours 28 minutes are passed from that point to now. That is where I need a measure to tell some time duration, count something. Okay, so let's get back here. What are the clocks I use in general? Okay, so conventional, let's go back. So the clocks should allow me to do two things. Number one is it should allow me to do count something. That is one. In what way it can count? Let's say there is some kind of a pendulum. Let's say my eyes are just closing and opening. It is just doing one rotation. Okay. Same thing the clock should be able to do. Okay. So let's say there is a beater. It starts from equilibrium position. It just beats one complete rotation. So that takes, let's say, 1 second to beat. So it just takes 1 second to beat. And so how many beats it is making, accordingly, I'll just define my duration. Okay. So a clock should allow me to count, that is one. And the clock should be able to do an oscillation or some kind of a activity in oscillations, so that how many oscillations it make, accordingly I can specify the time what I want. Okay, right? So that is the one. Fine. Okay, just a minute. Yeah, right. So the next thing is for most of the history, the oscillating mechanism have been human-made objects. Okay, means let's say I create a pendulum, it just oscillates, right? It just oscillates. Okay, so I can't expect the pendulum to oscillate forever. Okay, but the problem, why? Because of the gravity, the pendulum would come to steady state position. So I need to keep on giving the energy there, so that there is amplitude which ensures the oscillation. Okay, so let's say I use some kind of a spring to create that amplitude giving every time, right? And spring in time it get deteriorate. It's made up of metal, it deteriorates. So the spring may not have same internal energy, same spring constant forever. So that means there is a chance of error creeping in creating the oscillation. So initially it may be intact, a proper oscillation. Later on it might go slow. So in that case, I might go wrong in specifying the unit of time there for one particular oscillation. So that is what I was referring here. Every human-made objects are prone to error. Okay, and one more problem is, let's say I prepare two clocks. I prepare with same care, so I can ensure that two clocks are alike. So if there are any errors, they may creep in both the clocks. They may happen at the same time, right? Let's say somebody else prepared the same clock. Let's say something is done in China, something is done here. Probably the raw material being used or the care taken in China may be much less here compared to here. So the China ones may deteriorate in creating oscillations much faster than here. So if we, let's say we keep in sync, we want to keep time in sync, okay, right? Let's say I tell some collaborator in China that I will meet you 3.5 hours after the sunrise on Friday. Okay, and I presume that is at 3:30 or 9:30 or 6:30 or something. But there the clock is so much different because it is deviated from the actual scenario. So the time mismatch would happen. Okay, so the human-made timepieces can never perfectly sync. They drift away from one another. Fine. So these are the clocks for you. Now, can we get rid of the problem what I have, the synchronization problem? Is it possible? Okay, I don't want to realize something which is deteriorate. Let's say something which doesn't deteriorate. What I'll do, I'll go to very smaller core level, very small level atom. Okay, if I go to the atomic level, what happens is there is a chance the atoms are stable, by the way. Okay, so stable, if the electron which is rotating about the nucleus, even though it is doing lot of work running around, it never loses the energy. That is what the beauty of the nature is. Okay, that is what in fact led to the birth of quantum physics. 1900, before 1900, the experiments were done on the stability of the atom, and people were observed atoms are stable, and the classical physics rules which were saying at that time that something which is spending energy or going around should lose energy, should fall into the nucleus. That is not happening, because there are stable orbits, like Bohr said. If the electrons happen to exist in those stable orbits, or the orbits which are conserved, or which are called angular momentum is conserved in those orbits, are quantized in those orbits, they never lose energy. That's why electrons are staying. Electrons are nicely going around the nucleus without losing energy. Only they lose the energy, they go close to the lowest orbit, or they gain energy when they take energy from outside, go out. Okay, so at the atomic level, this is so close. And can we use those atoms for doing or creating a clock? Clock is what for me? It is an oscillatory behaving device. Okay, it should create an oscillation as many number of as I want, so that I can count a time as I want to specify a duration, an activity. Okay, so clock should be able to do many oscillations. But when I take an atom, it is having an electron energy ground state and an excited state. If I put the electron in the ground and supply a photon, electron would jump to excited state, and when they jump, it can't stay there forever. It has to come down, right? So by the time it comes down, I send one more photon, so this guy goes up. So it just does the oscillations back and forth continuously. Okay, so one oscillation, I can use it as a unit of a time, and how many oscillations it makes, I just specify in this number of times some duration time has passed. So atom is the best source to realize an oscillatory effect, a device which does the oscillation, and that device I can use to specify a time. Okay, so that is the idea. I think it came in 1950s itself, using atoms for creating a clock. So atomic clocks would come for a rescue of synchronization. Okay, so here I say they're perfect, create a perfect beats, and they don't have manufacturing parts because they're existing by nature. They don't wear out, they don't slow down, they have same specific angular momentum, same angular velocity electrons would have, they're stable. Okay, and moreover, all atoms are identical. If I choose cesium atoms to prepare a clock, all cesium atoms are alike, unless I don't go for its isotopes. Okay, so I can tell I am preparing atomic clock here with a cesium. I can tell somebody else somewhere in another country, you just prepare cesium atom clock, so both would be in sync. Only thing is, we have to start at the same point and then wait for time counting. Okay, okay, so the take home here is I would be using the transactions or atomic oscillations, Rabi oscillations I would call here, to count something in terms of a beats here. Beats, like a beater does this, a photon electron does this, up and down. Okay, now let me go to the next slide. Okay, now what I need further apart from atom, the another one I would be needing is a light source. Not any light source I would be needing. I need a light source whose energy is exactly equal to the separation of, okay, the separation of the atomic transition I am just choosing. That is one condition. Number two condition is I need that incident energy photon is in resonance. In resonance in the sense I was using detuning in the previous scenario. Okay, so now I need a hand note. Okay, so you see that is where I need. I'm not going for PPT. Sorry, presentation mode. Okay, so what I mean by resonance is, let's say incident energy is exactly matching, is in resonance. Incident energy is slightly detuned, not tuned, is called detuned. So there is a separation delta, which is equal to, let's say, incident photon energy is angular frequency is omega p, and transaction, if say this is 0, this is 1, 0 ket, 1 ket, and transaction is 0, 1, omega 0, 1. So there exists a non-zero value, means it is detuned. Not too much, remember, if you send, like this is, the separation is, let's say, 100 joules, okay? The incident photon should be something around 98 joules, or it can be 102 joules. Even that is also possible. But not like expect 100 joule separation, expect 80 joules photon to interact with that. That kind of a lot of large detuning doesn't work. Okay, why it doesn't work? You can just go for a classical, simple classical example. What I showed you here, uh, in this case, here you see the classical example of swing in a playground, right? Everybody might have played with this with the kids or somewhere in the lifetime. Okay, so here you see if the swing is coming towards you, when it is about to hit you, you would not try to push. You would wait unconsciously itself. You will wait until it comes and about to stop and then try to come down. At that time, you just push. So you keep on pushing in sync with the motion of the swing. In that way, you create a nice large amplitude by just giving a small tap at every time in sync. Okay, so that is what in resonance, that is what should happen for the incident light on an atom to have a nice oscillations, sustained oscillations from throughout. Okay, so the next requirement for atomic clock is the resonant light. Fine, right? And what are the like ticks in the atomic clock? Like what is ticking? Okay, that allows us counting. Okay, so one, like I said, oscillation, one complete rotation, or one quantum jump. It's called electron jumping from one to excited. If excited and coming back, that is one complete rotation, is one tick for me. Okay, so let's say by measuring how many ticks it does in a given duration, since it is fixed, it only takes certain amount of time every time it ticks. It is not like for, like say, now it takes 10 seconds, after hour it will take 15 seconds. It's not like that. A given atom, given energy in resonance, a light source, it always does it same fashion. It is fixed by that. Okay, so by finding how many oscillations it makes, I can come up with the counting technique. Okay, right? So, and one thing, let's say, and there is a crust and trough, there is a high and low, right? So depending on the number of high and lows completeness rotations it makes, I can just give us a number of ticks at the time. The question is, how many cycles of crust and troughs do we need to count to tick off 1 second? That is one question. So somebody defined us what is a 1 second for us, right? For a 1 second, if you are coming up with if you are coming up with a new unit, let's say you say 1 second, right? Second, let's say I would not say 1 second. I would say I will come up with a new unit called 1/3. Right? So second is the first and second. There is a third, right? I want to define a unit third. So what is that third? How much duration is a third? THIRD, third. So if you want to define, so you need to know in that 1/3, right? How many crust and trough I have to put in to define that 1/3. Okay. Then your time unit, the simplest unit is the third, and then you can find the largest, just like a seconds to minute, minute to hours. You need to define a third and something else, like in analog to a minute, something else to the hour. Okay, right? So you have to do that depending on the scenario, type of atom you are choosing. Okay, and depending on the frequency, resonance frequency light you are choosing, you have to figure it out, right? So, right? So let me go to the next slide. Okay, next. What is the time? I think I have to hurry. Okay. Right. So people started using cesium atoms to create that kind of a clock, which does the oscillations. Interestingly, if you just choose the cesium atom, it does those kind of a transitions, oscillations. In 1 second, it does 9192631,770 cycles of oscillations. That is what 1 second for me or for anybody currently. So that is so fast. The unit of my eye flip in 1 second, my eye flip is slightly different from somebody's eye flip, because somebody does very fast, somebody does very slow. So that is a mismatch there. If I choose this cesium 133 transition, cesium 133 is a isotope, particular isotope. For that isotope, if I send in some resonance frequency, it does how many oscillations? That many oscillations it does. Or this many number of cesium atoms would get excite and then come back. You can see it that way also. Okay, so this is started in 1967 to define 1 second in this way, a standard second. So prior to 1964, people were using orbital period of Earth. Okay, and they divided this orbital period in terms of some equal, I think something to do with the moon's transition or something. So that is prior to that. That was actually changing, by the way. Okay, so our speed is changing, its orbit is changing, all those things are changing. That means in time we would lose the synchronization, or we lose some accuracy. So cesium clocks have demonstrated stability about 2 parts in 10 to the power of 14 error. Only 2 parts. In 10 to the power of 14 parts, it just only makes two errors. That much accuracy it has. Okay, right? So that is 1 second in 1400000, 5 zeros. Within this years, it only misses by 1 second. That much accurate it is. Okay. Now let me go. Right? What is the cesium atom we are talking about? Right? So just don't bother too much about the text. This is for your reference. You can go through it later. I'll explain what it is. Okay. On the right side, what you see here is there is a cesium atom. Cesium atom is having 55 protons and 55 electrons. Okay, it's a neutral atom, right? Okay, so that means it can arrange all the atoms in its orbits. Okay, what you see here, I can move my yeah. What you see here, there are so many excited states. There is a first ground state. Let's say n equal to 1 is a ground state, n equal to 2 is excited, 3, so on. Okay, so depending on what kind of orbit it is, s orbit or p orbit or d orbit or f orbit, I can put certain number of electrons in them, or not me putting, nature itself is putting. So by the time you go to the outermost valency orbit, all of them are arranged in paired version, means equal number, even number, and there is only one electron which is left out, which is going to occupy in 6s orbit. Okay, now that's a lone guy. Okay, that lone guy, what that guy does, since it is a lone unpaired electron is there, that guy contributes all sorts of things. He will make it's a conductor, and he is very responsive to the magnetic field and electric field because of that lone electron is there. If that guy is paired with somebody else, he would not do anything. Okay, since he is unpaired, he has all sorts of dynamical behavior. Now, because of that, what happens is on the bottom here you see this electron guy would experience the magnetic field due to the electrons which are there in the lowest orbit. That is possible. And this electron could also experience the magnetic field of the nucleus. And this electron could experience the orbital angular moment Orbital angular momentum is magnetic field coming out of the electrons which are going inside the orbit. Okay, what I mean, I quickly draw the figure and show you, right? So if there is a nucleus, if there is an electron going in an orbit, so electron is going like this, electron is going in this way, anti-clockwise. Clockwise would constitute a current. So whenever I have a current carrying loop, clockwise, so the magnetic field would be inward. Okay, cross symbol. Magnetic field going into the board. Okay. Now there are electrons here, but this electron is outside. These electrons could affect this guy, but not much. Okay, because it is very minimal, and moreover they are paired. Whatever magnetic field this one guy is creating, it is get nullified by other guy. That is how they are connected. That is how they are paired. One is upspin, one is the downspin. That is what the pairing is done. That is how the electrons pair up in a given orbit. But the effect of every guy got cancelled, but only the guy which is nucleus. Nucleus is alone, is very huge. So this guy has its own spin magnetic moment. This guy would induce some effect on the electron. Because of that effect, if you have something which is magnetically responsive, if there's a magnetic field applied, that guy would respond to that. Okay, it is like I have a bar magnet which is arranged, sorry, a bar magnet, or even if you say compass. Okay, there is a compass if you have. Okay, so if the compass is there, compass means what? A small needle with a north and south. It's just a simple bar magnet. If there is a magnetic field lines which are coming just like that from a large bar magnet, okay, large bar magnet, north and south, the field lines would be going like this, goes out and goes in towards the south. Now what happens? The compass would try to align for the field line. Compass would become like this, try to arrange. Okay, that is the nature of the magnetic fields. Okay, now it is trying to arrange, right? What I will do on the right, I'll have one more bar magnet. I'll just put NS again. Now what happens? The field lines are going like this. Okay, what this guy does, he wants to align as per this guy, and it will try to come here. So north here, south here. If I have space both sides magnets perfectly, what I can create a rotating compass. Okay, right? That is the effect on the north, on the simple compass. Now the strong magnetic field is created of the rotating nucleus. Nucleus is rotating itself. Okay, and there is a, let's say the nucleus magnetic momentum is appearing like this, north and south. There's a north south, there's a small bar magnet, and there's a small bar magnet here of the electron. The magnetic field lines are like that. Okay, so this guy would feel the magnetic field lines, right? And so that's so far, right? So this guy at a given point is a quantum in nature. At some point he would be pointing up, at some point he will be pointing down. Okay, it's a superposition. So there is a pointing up, let's say some excited state energy level, pointing down is a ground state level. At any given point, this guy can be here or here, the electron, because of the induced magnetic field due to the nucleus. So that is what you see, the splitting of the hyperfine splitting of the electron into two states, where this small red arrow you see, that's a downspin, up arrow is called upspin. So electron can be in both the states because of the magnetic field created out of nucleus. The 7/2 nuclear spin you see, that is very large. Okay, at any given point it can be in F is equal to 3 state or F is equal to 4 state, the electron. What I will do, I can use this transition, whether going from upspin to downspin, as a beat, as a transition where I can beat and count the duration. Okay, that is the idea for the cesium. Okay, and there are a few more remarkable facts. I just said the cesium is having 133 number of protons plus neutrons. Okay, so protons is the one which decides the atomic number. Protons is the one which decides how many electrons it should have by default. I can add one more electron, it becomes ion, by the way. Okay, naturally it should have how many number of protons, and neutrons are just a neutral particle. I can add, I can create an isotope out of it. Okay, so 54 protons, sorry, 54 electrons which is it has, they're all arranged within the lowest orbits. The last one is going to outermost. That is what the xenon 54 core, symmetric core I mentioned in the figure. Okay, right? And whatever I was explaining earlier, that is there in the next slide. Okay, okay, just a minute. Okay, so, and one more thing, it can work around 100 degrees Celsius, right? Why I'm talking about is the with 100 degrees Celsius, there is an amount of energy which is given to the cesium is 0.04 electron volt, right? So that means there is no need of cooling, right? Okay, and that is what this slide is talks all about. Okay, just a minute. Okay, let me, yeah, remarkable facts. So there is a temperature I'm talking about, how the transition energies. Okay. Now, the age of atomic clocks right now. So it started very, very early from 1947. Okay, from there, people trying to improve the accuracy. Okay, so they have started with atomic clocks. They went on to do, okay, just a minute. Yeah, right. So they went on to prepare different kind of atomic clocks, something called beam clocks, something called uh, uh, just a fountain clocks. Okay, there is optical clocks. This is all we will discuss tomorrow, and we'll discuss the next topic also tomorrow, which is the, let me tell you what is that, the state of the art of quantum sensing. Among that, we'll discuss about magnetometers, and gravimetry, which detects gravitational fields, and also there is a NV center based sensing, that is one of the state of the art. We'll discuss those three things, and we'll finish the atomic clocks in the first half an hour. Okay, I'll stop here, and if somebody has any doubts, please let me know.
Yeah, if there are any doubts, participants can ask. You can type in the chat. Right, we are starting the exam from today, but you don't have to attempt today. So you can attempt tomorrow, you can attempt on Sunday, you can attempt on Monday till 5 o'clock. Few people, they want to finish today itself, so you can take the exam. But I think Ashwath sir may have given some questions from tomorrow's class also, right, sir?
Not much, I would say.
So I think from today you can take the class. I informed sir.
Atomic clocks,
so,
yes. Atomic clocks, yes.
yeah. So
Yeah.
till today's lecture will be there. So don't, maybe you can prepare, refresh today, and then take the exam. If some other work you have, so you can complete the exam today. So maybe by 5:30 or 6 o'clock, we will post it on Canvas, and then any time that you start, because there are, I think, 25 questions this time. Right, we will look at 25 or 30 questions. So accordingly, we'll set the time. One email will come to all of you. So please, and then based on that, you can, of course, go to Canvas. I will put in the group also the time, duration, and till 5 o'clock on Monday, you can take the exam. Tomorrow, Ashwath sir will take the first 2 hours. Then we have the lecture by Mustafizur Rahman, who will take from 4 o'clock to 6 o'clock. So please join, please plan your tomorrow schedule. It will be till 6 o'clock, 4 hours. So with that, we'll be finishing full 40 hours session. It will be, even Mustafizur Rahman will also do as much interactive as possible. So please be ready for questions. He's a PhD in quantum related work, and also is working with IBM on quantum. So what is the industry questions and all, you can ask him, and you can get the doubts clarified. So both the lectures are very important tomorrow. We were thinking of somehow managing the farewell also. Farewell means valedictory session, but I'm not sure. We'll see how it goes. I will request Mustafizur Rahman to give us half an hour so that we'll conclude with some thanks, vote of thanks. We will take your feedback. Some of you can jot down the feedback and send it to us of what improvements can be made. And, of course, we can also give some feedback about the faculty members as well. We will float a feedback sheet also. We are taking that feedback sheet, you will fill it. So quiz 2 will start. So both the quizzes, those who have attempted, okay, please note that is one slide is not uploaded. Yes, Professor Venkat, Dr. Venkat Subramaniam's slide is not uploaded. We will do that shortly, except that I think all others are uploaded. Today, once sir shares the material, I will upload, or in fact, sir is uploading himself. So we will, please go to the files, and under files, you will find lecture material. Under that, you will find Dr. Ashwath's slides, or slides of Dr. Ashwath, right? So please open that. Sir is putting a PDF of the entire content, handwritten content that is there, and the class running notes also he is putting. That's an image. And of course, he is providing some additional files or pictures like that. There are additional files. So you will see the lecture and the number, that will be the lecture slide. Note